In this video, I'll be talking about pH, pOH, pKa, pKb, and pKw, and how each one of these terms interrelates. In a previous video, I had mentioned that water autoionizes to form the hydronium ions, H3O+, and hydroxide ions. Now, because water breaks apart to form those two ions, in neutral solutions, ones that don't have an acid or base added to them, the concentrations of the hydronium ions and the hydroxide ions are the same. At 25 degrees, the concentration in pure water is 1.00 times 10 to the negative 7th for each. Acidic solutions are those that have a larger concentration of hydronium ions than hydroxide ions. Again, at 25 degrees Celsius, that would be the concentration of hydronium ions is greater than 1.00 times 10 to the negative 2nd, making the concentration of the hydroxide ions less than 1.00 times 10 to the negative 2nd. Basic solutions are ones that have a larger concentration of the hydroxide ion, OH-, than they do the hydronium ion, H3O+. So for basic solutions, the concentration of hydronium ions, H3O+, will be less than 1.00 times 10 to the negative 7th, and the hydroxide ion concentration will be greater than 1.00 times 10 to the negative 7th for solutions that are at 25 degrees Celsius. When we're talking about acidity or basicity often use or are expressed in terms of pH. The P in pH essentially is telling us that we're taking the negative log of whatever follows the P. So px means taking the negative log of x. So if we're looking at pH, it's the negative log of the H concentration, or in this case, H3O+. Essentially what we're attempting to do is look at the exponent that is on the 10 in scientific notation. So if we're looking at a neutral pH solution where the concentration of the hydronium ions is 1.00 times 10 to the negative 7th, then the pH of that solution, when we take the negative log of it, would be 7. So we're taking the exponent on the scientific notation and taking the negative of that exponent. What this allows us to do is have a positive number that indicates the relative concentrations of the hydronium ions in solution. So the closer the pH value is to 0 or 1, the more acidic the solution is going to be. So if we look at a variety of common substances, for example, human blood has a pH of 7.3 to 7.4. What that means is the hydronium ion has a concentration of 10 to the negative 7.3 to 10 to the negative 7.4. For wines, which have a slightly sour taste to them, and if you remember, acidity has a little bit of a sour taste, wines have a pH of 2.8 to 3.8. So the concentration of the hydronium ions would be 10 to the negative 2.8 to 10 to the negative 3.8. Things like limes and lemons, which are very sour, have fairly low pH. Right? The pH value of limes is 1.8 to 2.0, and for lemons it's 2.2 to 2.4. So the concentration of the hydronium ions in each is, for limes, 10 to the negative 1.8 to 10 to the negative 2.0, and for lemons it would be 10 to the negative 2.2 or to 10 to the negative 2.4. So for solutions that have a pH that is less than 7, what this is essentially saying is that the concentration of the hydronium ions is greater than what you would find under neutral conditions. Right? So the exponent on the concentration of the hydronium ions is going to be greater than 10 to the negative 7th. The way that we would then figure out the hydronium ion concentration is to undo that negative log process. So our hydrogen, or our hydronium ion concentration, our H3O+, would be equal to 10 to the negative pH, right? The negative here undoes the negative on the outside of the log, and the way that we undo a log is by taking the number and having it 10 raised to that value. Because we're talking about logs and measurements, one of the things that we would be interested in doing is being able to determine the number of significant figures in a value, and being able to take a pH reading and get an accurate concentration to the correct number of significant figures. So the rule for significant figures with logs is when you take the log of a number written in scientific notation, the digits before the decimal point come from the exponent, and the digits after the decimal point are the part that form the number. So if we took like the log of 2.0 times 10 to the 6th, the rule of logs is if we take the log of two numbers multiplied together, that's the same thing as taking the log of those two terms independently logged and added together. Right? So the log of 2.0 times 10 to the 6th is the same as the log of 10 to the 6th plus the log of 2.0. The log of 10 to the 6th is 6, and the log of 2.0 is 0.303030 repeating. So adding the two together would give you the 6.303030. The way we figure out the number of significant figures for a value that we're taking the log of is essentially the value that's raised to the 10 is the number in front, and the value at the beginning of the scientific notation tells us how many decimal places after that value are going to be significant, right? So if we take the log of 2.0 times 10 to the 6th, this first 6 comes from the exponent, and then because we have two digits in our scientific notation, we accurately know two of our decimal places, right? So the log of 2.0 times 10 to the 6th would be 6.30 to the correct number of significant figures. Essentially, the number of values in the first part of your scientific notation is the number of decimal places after your dot, right? So the number of values here is the number of decimal points after your ones place that you have that are significant. You can go in the reverse direction. If we're taking 10 raised to this value, the 6.30, going back into scientific notation, this 6 tells you what the exponent is on your 10, and then the 0.30 tells you how many digits are accurately known that will be in the first part of your scientific notation. So, what does the pH number imply? A lower pH value is one that is a more acidic solution. The higher the pH, the more basic the solution. 1 pH unit corresponds to a factor of 10 difference in acidity. So the difference between, in terms of concentration, a pH of 6 and a pH of 7 is in the pH 6, the concentration of the hydronium ions is 10 times greater than a solution with a pH of 7. Under most conditions, you'll normally see values for pH ranging from 0 to 14. A 0 pH would be something where the hydronium ion concentration is 10 to the negative 0, which is a 1 molar solution. For solutions with a pH of 14, the hydroxide ion concentration will be 1 molar, and the concentration of the hydronium ions will be 1 times 10 to the negative 14th. Now, just because normally you'll see a range of pH values going from 0 to 14 doesn't mean that that's the upper and lower limits. Under some conditions, you can actually see acidic solutions with a negative pH. Recall that the pH, all that means is the negative log of the hydronium ion concentration. So if we had a 10 molar solution of a very strong acid, it's possible that we could have a hydronium ion concentration in solution of 10 molar. If you take the negative log of 10, that's -1. So under some conditions, you can actually have pHs that are in the -1 range. Similarly, you can have solutions that are very basic, where the concentration of the hydroxide ion is very high, making the concentration of the hydronium ion very small. So if you have a solution where the hydronium ion concentration is less than 1 × 10 to the -14th, you could have a situation where the pH is less than 14. Another way of expressing acidity or basicity of a solution is the pOH. It works the exact same way as pH, right? The P just means negative log of whatever follows it. So pOH is just the negative log of the OH- concentration. What we can do is we can recoup the hydroxide ion concentration by taking 10 raised to the negative pOH. Now, the pOH for water, right, would be the negative log of the hydroxide ion concentration in water. For a neutral solution, the concentration of hydroxide ions are 10 to the -7. So if we take the negative of the log of 10 to the -7, the value for pOH would be 7. In order to find the pOH, we need to know the hydroxide ion concentration. Once we know the hydroxide ion concentration, we can find the pOH. pOH solutions are sort of the reverse of pH solutions, right? The pOH, if the pOH is less than 7, that means that we have an elevated hydroxide ion concentration, which would conversely mean that we have a diminished hydronium ion concentration. So if the pOH is less than 7, then we have a basic solution. If the pOH is greater than 7, that means we have a very low OH- concentration, so the solution would be acidic. And pOH equaling 7 is neutral at 25 degrees Celsius. What you'll find is that the pH plus the pOH are equal to 14. That relationship comes from the fact that the concentration of the hydroxide ion and the hydronium ion are coupled together based on the Kw. So because water autoionizes to form hydroxide ions and hydronium ions, and the value for that equilibrium constant is 1.0 times 10 to the -14th, if the concentration of one of them goes up, the concentration of the other one goes down, and vice versa. Because we're talking about pH and pOH, we can take the negative log of both sides. So we're taking the negative log of the Kw, that being equal to the negative log of the H3O plus times the OH-. That gives us the negative log of Kw is equal to the negative log of the product, or multiplying together, of the hydronium ion and the hydroxide ion concentration. This would be equal to the negative log of 1.0 times 10 to the -14th. Negative log, we can replace that with P, right? Because P means negative log of whatever follows it. So pKw is the negative log of Kw. One of the rules of logs is if you're taking the log of two things multiplied together, it's the same thing as the log of each one independently added together. So because we have the negative here, it would be the negative log of H3O plus the negative log of OH-. Or you could express that as the negative log of the hydronium ion concentration minus the log of the OH- concentration. When we take the negative log of 1.0 times 10 to the -14th, that value is 14. So what this tells us is the pKw is equal to the pH, which is the negative log of the hydronium ion concentration, plus the pOH, which is the negative log of the hydroxide ion concentration. And that value, the sum of the pH and the pOH, is 14. Now, this concept of P is not just limited to pH, pOH, and pKw. We can also apply it to the acid dissociation and the base dissociation constants. So pKa and pKb are the negative log of the Ka value and the negative log of the Kb value, respectively. Just like with the pH and the pOH, we can get back our initial values by taking 10 raised to the negative of the P value, right? So we can get back our Ka by taking 10 raised to the negative pKa, and we can get back our Kb by taking 10 raised to the negative pKb. So the stronger the acid is, the smaller the pKa will be, right? Because our pKa is the negative of the log of the Ka. So if Ka is close to 1, then the negative log of that value will be closer to 0, right? So it will be a small value. So the larger the Ka, the smaller the pKa, because the relationship between the two is the negative log. The stronger the base, the smaller the pKb will be. The larger the Kb, the smaller the pKb. For polyprotic acids and polyprotic bases, because they have a number of different acidic protons that they can either give off or receive, we're going to end up having multiple values for the Ka and the Kb. The way that we're going to represent those is with a first, second, or third value, right? So that would be a 1. So Ka1 for the first acidic proton, Ka2 for the second acidic proton, Ka3 for the third acidic proton. Now we can also have pK values that correspond to each acid. So the first hydrogen that comes off would have a pKa of, we'd call it pKa1. The second acidic proton would be assigned to pKa2. The third acidic proton would be pKa3. Just like when we were adding together the equilibrium constants in a previous video, where the Kw was equal to Ka times Kb, essentially because we were adding the two reactions together, the acid dissociation reaction and the base dissociation reaction for the same conjugate acid-base pairs. And we saw that the Kw was equal to the hydronium ion concentration plus the hydroxide ion concentration. We can use the rule of logs here to come up with a relationship between Ka, Kb, and Kw. So the rule of logs is that the log of two things multiplied together is equal to the log of each independently added together. So if we take our expression that we have up here, where Kw is equal to Ka times Kb, we take the negative log of both sides, that would be the negative log of the Kw, is equal to the negative log of the quantity Ka times Kb. We're using the rule of logs up here to break that the product apart, giving us that's equal to the negative of the log of Ka plus the log of Kb, that whole quantity times that negative sign. Distributing the negative in, we get negative log of Kw is equal to the negative log of Ka minus the log of Kb. Again, the negative log, we can re-express that as just P, right? So the negative log of Kw is P Kw, right? P just means negative log. So the pKw is the negative log of Kw, pKa is the negative log of Ka, and pKb is the negative log Kb. So our relationship that relates all these terms together is the pKw is equal to the pKa plus the pKb. Now that works only for the conjugate acid-base pairs, right? So this would be the pKa of the acid dissociating plus the pKb of the conjugate base coming back to the acidic form. The summation of those two values is equal to your pKw.